Okay. Perfect. Alrighty, I can see it. Alrighty. Wolfgang, are you good to start?
I'm good to start. I don't see anyone anymore now that the screen's shared. So if anything comes up, you just have to speak in the microphone.
I'll let you know if someone's making faces.
Okay.
That works.
Yeah. Okay, so thank you everyone for being here again for another of our seminar talks on interpretable deep learning. Today we have Wolfgang Stammer, who is a postdoctoral researcher at the Max Planck Institute for Informatics. And he's going to be talking about inherently interpretability via compositionality, from encodings to reasoning. Sorry, I butchered the title, but please take it from here. And yeah, thank you so much for being here today.
Thanks so much. Just to double check once, can you see my mouse when I move it?
Yes.
Okay. Okay. Then yeah, thanks for the introduction and thanks for the invitation. I enjoy this seminar series. I'm very happy to also speak some of my opinion on these topics. Just briefly, who am I? So previously I was a PhD in Christian Kersting's lab and TU Darmstadt, working kind of on the intersection of explainable AI, interactive learning, and neurosymbolic AI. Now, since October 2025, I am a postdoc in Bernd Schieler's department at the MPI for Informatics, which is in the computer vision and machine learning lab or department. And now I'm very much interested, it's still somewhat related, but focusing more really on this compositional reasoning in AI. Now, this includes multiple topics: A, like discovering compositional representations; B, how to integrate compositional representations into AI models; and then C, also how to actually then reason over these representations. And within all of these topics, there are like multiple perspectives from understandability to controllability, but also to generalization. Now, I mean, the overall problem, I think everyone is aware of this in the seminar series. I'll just briefly recap it just to set the stage. So high-performing models are great, but often opaque, and particularly in high decision domains, I argue, especially I want transparency and control. And not so much everyone wants it, but I think it's very worth looking into how we can still have both. Now, the big limitation, I mean, you could just go for a fully interpretable model, but this can be quite impractical in complex tasks and inputs. They might not be as expressive, or they might actually be so fine-grained, it's just also difficult to understand them. So in essence, I think what I and also many other researchers, I think particularly in the seminar, are interested in is building expressive, generalizable learners, but that still allow for understandability and controllability. And potentially what this then requires is that you need these different levels for tasks. And so what I want to kind of talk about today is some like a common kind of theme I've been identifying in a lot of research, and also like putting into some of my research with my co-authors, which is a lot of interpretable kind of by design models, or also in this context, many neurosymbolic approaches. They share a kind of common implicit assumption, which is that models should decompose the reasoning into structured, ideally human understandable parts. And so this compositionality aspect is often kind of the mechanism behind all of this, but it's rarely named explicitly. So what I want to talk about in the next section, and I'll see how much time I have. I have a few papers I want to discuss. I probably have to drop a few in the end. But is kind of the question, what is the right unit of composition for interpretable reasoning? And what we'll find along these papers I'm discussing, that this does not have a single answer, but it usually kind of depends on the task, the input, and the level of transparency you need. So I'll just dive right in. So I think one of the most basic decompositions I've seen, and also many people have worked on, is this task decomposition. And this is very prominently seen in the concept bottleneck idea, where you decompose a task into usually two parts. It's kind of the basic structure, where you try to route predictions through human interpretable concepts. You kind of have this two-stage structure. First, you have your input, which goes through an encoder, which gives you some kind of latent representation, ideally tied to some human understanding. And then you have a prediction part, which given this latent concept layer makes a task prediction. And within all of this, you kind of have this Markovian assumption that the output is independent of the input given these concept representations. Now, recently, there's been actually quite a surge on these concept bottleneck models, I think largely attributed by the benefit or the potential of using foundation models to make this concept sourcing and grounding scalable. Now, why does this task decomposition help? Well, there are actually several aspects just by adding this one kind of in-between layer, this one level of decomposition. You get an explanation on this decomposed set, giving you kind of what concepts are relevant for a task, but also with what strengths. You can intervene on this intermediate layer, potentially doing kind of interventions of asking, if I change this, what happens now to my decision boundary? And this allows a lot for debugging. So for example, for human-in-the-loop settings where you want to really identify, okay, is the model doing the right thing for the right reasons, so on and so forth. Now, in a recent survey, me and also several colleagues, we had this issue that by now there are so many papers on CBM, it's kind of difficult to identify what are really the different components of all these papers. So we created a recent taxonomy in a survey paper, which I can recommend, discovering kind of this taxonomy of many different parts that you can identify in CBM approaches, some focusing on the input module, which kind of gives you the actual input embeddings, another module focusing on the actual concept representation, and then a third module focusing really on the prediction part. And now different approaches, they instantiate these components differently. And what kind of one let's say, conclusion to be drawn maybe from this is the CBM landscape has grown very rapidly. But what we also identified was that in like approximately 80% of the approaches, most models, they rely on really flat, almost global input embeddings. So they're essentially treating the entire input as a single unit. And this works, for example, in the image domain, it works very well for like single label image classification. But essentially, by having only this one global layer of concepts, you're also limiting to what the concepts can express. So if you're interested in more complex tasks than just single image classification, you're kind of screwed. So the question and the next work we'll be focusing on is kind of what's the right unit of composition for visual tasks. And I think a very natural answer to this is actually to have object level decomposition, not just full image encodings. So essentially the idea we have here in this paper called Object-Centric Concept Bottlenecks is to integrate object-centric concept representations into the CBM framework. Now, object-centric representations are, the different ways of doing this. Essentially, the whole idea is you're grounding information to specific entities within your image. And by doing so, you have this kind of explicit grouping of information. And one idea in this work was to use the power of recently, pre-trained object detection approaches, such as SAM, so these kind of foundational models, which already do this quite well. And the idea is pretty simple. So still within the CBM framework, you get an image, you encode it, you use some kind of concept extraction method. In this case, we're using Splice from Bala et al., which essentially is based on clip similarities, but they still have some sparsity optimization within this. But this essentially gives you the scores of different text level concepts. Now, what we add is quite simple. Before the actual concept extraction part, we do a set of first identifying parts in the image, which would correspond to objects using object proposal model. We use a specific refinement kind of filter mechanism to filter out maybe two big object proposals or two small object proposals. These are hyperparameters of the network. And then we crop out these objects, and then we pass these additional images through the concept discovery or the concept extractor giving us now actually multiple concept encodings, one for the global image level and one for each kind of crop individually. Now, also, like the first author, David Steinman, already had, I think, a seminar on this previously, so I'm not going to go into too much detail on this part. But now we need to aggregate these separate concept encodings into one joint concept encoding. There are different ways of doing this. And then we make the final prediction based on this aggregated concept or object concept encoding. Now, the kind of the takeaway message I want to make here is showing kind of the results on multiple, actually more complex reasoning tasks. So in this case, multi-label reasoning tasks compared to only single-label reasoning tasks. But then also more logically complex single-label reasoning tasks like Coco logic. We see quite a substantial boost when using these object-centric concept encodings compared to the vanilla kind of flat encoding baselines. Here we also show that it's somewhat independent of which kind of object proposal method you're using. The RCNN is, of course, a little bit more fine-tuned for particularly these kind of Coco-style images, but also when using a really general SAM foundation model, you still get substantial improvements. And so by doing so, by kind of having this object decomposition, we also allow to move towards these more complex visual tasks and these more complex reasoning tasks. Now, apart from the actual like performance accuracy, there's of course always the idea that this also allows for more fine-grained explanations and analysis. So looking at the bottom part here, now we can allow for counting tasks, but we can also identify which object particularly has maybe contributed to some decision. Or also on the top, we also get much more or like new concepts by integrating this object bias into the model. So all in all, just to summarize this very quickly, so these object level representations give us richer, more grounded concepts, particularly for more complex visual classification tasks. However, so this is cool, but classification is still a static task. I would argue also, I think it's time to like move away from classification. And many real world settings are actually dynamic. So looking in like what I'm around here, an agent must like act and interact with the environment, observe consequences and like adapt over time. And in these settings, you actually need more than just the object properties, but actually a lot of the information, relevant information, is stored in the relation between the objects, not just the objects themselves. So looking into the next kind of approach, the next kind of project, we were wondering, okay, what's like the best unit of composition needed to integrate these ideas also to such like sequential decision-making settings. Where we focus on deep reinforcement learning agents, in this case, kind of within the Atari game environment, where, I mean, also here you have the issue that like the standard post hoc attribution methods only get you so far in understanding these deep RL agents, and particularly looking at kind of shortcut cases, which I'll discuss in a bit, these kind of explanations don't help much. So also here you want this decomposition, but again, so the object decomposition is not enough. So this is the overview of what we're introducing here. So together with Quentin Delfos, published in 2024 at NeurIPS, the Successive Concept Bottleneck Framework. It's also quite a simple idea, I believe. We still use object concept representations. So like per object, we get specific concept encodings. But now what we're adding is relational functions between all of these objects. Now, actually, in this framework, these functions are predefined, and they're somewhat generic for all the Atari games. And these can either be given by a human user, or we actually also show in the paper, to some degree, this also works quite well to have an LLM just propose these functions that you need for the game, given you provide additional background knowledge a little bit, but it seems to work quite well. Now, another point to make, this is not so much on the compositionality part, but what we do differ here in most standard CVM approach is that the predictors, in this case, the action predictors telling the agent kind of which move to make in the next step, is not a linear layer, as in standard kind of CBM approaches, but what we do here is we first train a neural network, a nonlinear neural network, and then we distill a decision tree from that nonlinear neural network. Now, again, within the CBM framework, you still have the ability to kind of interact with the system, but now not just on the object concept encoding level, but now also on the relational encoding level. And I'll show a few examples on this. So comparing now across like very diverse kind of games within this entire Atari environment, and using a deep RL agent as a baseline, we see that the SCOBOTs, so with this multiple kind of concept bottleneck idea, plus a decision tree in the end, is as competitive or sometimes even better than the deep RL agent across these very diverse games. And now this is, I think, one of the kind of the cool findings from the paper also, and I think this also very much motivates the whole idea of having this decomposition, is that we found a very strong shortcut in one of the simplest games at all, which is in Pong. And apparently what happens is that the enemy paddle is strongly correlated with your paddle, or with like the player's paddle. And so the agent playing actually just focused on the enemy paddle to make its decision on where to move rather than the ball, which you can argue is kind of not what you want. So what we did was we created, just to test this hypothesis, we created like an alternative Pong environment where we actually hid or like occluded the enemy paddle. The ball was still visible and the enemy paddle was still playing. But what you see is that the kind of the RL agents, the deep RL agents, they just fail all of a sudden, although they were very good previously. And we could like analyze this because we saw that what the agent is most focusing on to make its decision for a move is actually the distance between the player and the enemy paddle. So by having this decomposition, and not just on the object level, but also on the relational level, we could identify this error. Now, a human user with such SCOBOTs doesn't have to say, okay, I have a wrongly trained agent, but you can actually correct the agent by just kind of pruning this relational space, or maybe even updating the object space. And now you have these two levels of interaction, which you did not have previously. And we have some other examples in the paper with particular like RL kind of based failures, like sparse rewards or misaligned rewards. And also there, by having this kind of relational axis or decomposition, it's much easier to mitigate these issues and identify them in the first place. So to summarize this section, by adding kind of this additional relational decomposition, which we did not have previously, we could move the kind of the tasks which we can solve or play with to a much bigger realm. At the same time, still allowing for this this understandability and also intervenability aspect which we had previously. Now, kind of one, I guess, issue with these kind of approaches is still, like, as I mentioned, the functions were predefined. Even if you have an LLM, this doesn't always work if it's like too out of scope for the LLM. So the questions we asked next is, what if we don't have all this pre-trained knowledge? How can we get the right relational concepts? Maybe we can even compose these relational concepts based on the data rather than specifying them beforehand. So moving on to the next project, this is what we then looked at. So how can we learn to compose these concepts, but in a principled and like reliable way? So this is, I think, the limitation I just previously discussed is actually, I think, something we still see in quite a few CBM approaches, that you still require some amount of human prior knowledge on like what concepts exists, what matter. Again, I think a lot of people are using DLMs nowadays to kind of mitigate this, using the pre-trained language alignment of these models. Here we were asking, can we learn this, like these compositional relational structures without using too much knowledge, but still in a principled way? One reason for this is that where VLMs tend to have pretty like rich perceptual capabilities, they sometimes fail at these very systematic visual reasoning approaches. So for example, in inductive reasoning, where you're trying, for example, here to learn from multiple examples of positive and negative sets, and you're trying to identify the rule which distinguishes the positive from the negative ones. What you tend to see is that a VLM can, of course, generate a plausible sounding rule, but these can, and at times they do often violate kind of the examples that they're actually seeing. So there might be multiple reasons for this. I think one of them is the well-known kind of hallucination part, where it's actually not identifying the right things, or it's identifying things which are not there. So here in this project, I just actually recently presented at CVPR together with Antonio Wüst, is instead of using VLMs to do the full thing, so perception and then the kind of the downstream reasoning, why don't we use the VLMs for the perception side, but then somehow like outsource this reasoning part to maybe a more principled approach. And particularly here we investigate the potential of structured program synthesis, which essentially searches over a program to best cover the examples it's seen, and couple this with the perception abilities of foundation models. And why are we doing this? So there's multiple reasons. Programs can be executed, and so they can form a very kind of natural way to mitigate some of the faithfulness issues, for example, that many like language-based chain of thought processes have. At the same time, when you do like this principled search, you have more guarantees on that the output that you're getting, the kind of the best program you're finding, is indeed like the best program given your input. So this is a big figure of what we're introducing, so that we call it the Vision Language Program Framework. I'll just go through them step by step. I know I'm kind of rushing through all of these things, so if you have questions on the details, please feel free to ask afterwards. I just wanted to get more of the high-level idea across here. So in the VLP framework, what we do is we start still with a symbol grounding part. So we want to identify what are the kind of the relevant symbols, in this case, objects, properties, and actions within our images. And here we use the VLMs. So we kind of query the VLMs. What are, given all these sets of images, you have here 6 positive, 6 negative images, what are potentially relevant properties, objects, and actions? And this gives you kind of your initial dictionary of symbols. Now, to do a search, like a structured search over possible programs, you need so-called domain-specific language. This is kind of like a grammar, similar as you have in natural language, something telling you, okay, like the common relationship between verbs and nouns, or adjectives and verbs. The DSL gives you this kind of structured kind of grammar. And there are multiple components in this DSL. I'll talk a little bit on the next slide on the details of this. But essentially, given the symbols we receive from the VLM, we now actually like bring the functions in our DSL to life by kind of integrating the symbols into these functions. And this altogether then represents a domain-specific language. Now, in the third stage of the framework, given this domain-specific language with the instantiated symbols, we now do a really structured search over all the possible combinations of a program given the input positive and negative sets. So this is really, you're trying to combine and recombine parts of this DSL into a full program. And by doing this search, you get out the final kind of most probable program, which allows you to differentiate now between the positive and negative sets. Why is this cool? So again, because this program can be executed, each function in this program is an individual function, either a call to the VLM asking what are the objects in this image, or this is like a list processing function, just mapping, or like not mapping, processing over this list. So just here's a kind of example of this DSL part. I think for many people who are not working on this, it might be a little abstract. But so the DSL defines functions, VLM functions, symbolic functions, but then also program operators. I briefly mentioned the VLM functions are queries about objects, properties, actions. So like given an image, we would query the VLM again with a prompt. What are the possible the actual kind of things we're seeing in this specific image from the set of possible symbols we discovered previously. Then the symbolic functions are essentially more like list processing functions. These are more basic functions and not, or they're static functions, let's put it that way. And then the basic operators are usually, logical operators and that kind of thing. Just the basic operators you need to actually usually combine a program. So then the program search is guided by a probabilistic context-free grammar, where you can do this in different ways. So for example, just define a uniform probability over all the possible symbols and functions. What we do here is actually have a kind of data-driven probability distribution, where given your specific input set for your task, specific symbols might be more probable to occur across all the images, so they might have a higher probability. And these probabilities in the end kind of guide your, in this case, we use a heap search approach across all the possible programs. And by combining all the programs together, or all the individual components together, you get the final probability. The final program with the highest probability is then selected. And then you can actually just, again, run the program over your given input, where each function is executed on the image, giving you, like, for a new unseen example, telling you whether this is a positive or negative set based on what you've seen previously. So why is this cool? So essentially, this is a different form of reasoning also. This is kind of a program-based form of reasoning versus natural language-based reasoning. And here in this table, we see that across 5 different open source VLMs, these are instruction-tuned models. When you actually integrate these within the VLP framework, you get quite a huge boost in solving these kind of complex learning by example paradigm settings. So these are natural language images, sorry, not natural language, real world or natural images within this positive negative set kind of paradigm. Also some synthetic images. And so you see also here the benefit is we don't need to train individual perception models anymore. We're just using the VLM's abilities on this perception part across all these domains. Also, the DSL is the same across all the domains, but we see quite a large boost. And now also comparing with actual, I think people call this differently, but thinking or reasoning trained VLMs or fine-tuned VLMs, we see that we get a substantially higher performance on most of these tasks. Even though in this comparison, the VLM, so in this case, Kimi, for example, with the VLP baseline or approach, is an instruction-tuned model compared to the thinking fine-tuned model. At the same time, we also see that this comes with substantially lower computational costs, so we need a lot less tokens than if you do like the standard kind of chain of thought processing. But, and this is also quite important, we're not saying they're this form of reasoning is exclusive, but rather is kind of orthogonal. You can actually combine the two to get the kind of the best of both worlds, then potentially kind of getting, again, a higher computational cost. And so now this is, again, I think another important part of the whole story is by having this structured kind of solution space from which you're trying to identify the best solution, you again have the possibility of interacting very well as a human user. And again, these programs are readable, even though like the initial language, so we're using a functional programming language, it's maybe not the most intuitive one for most people, but still you can like read these functions and execute them. And now in this case, focusing on the Clever Hans data set, which has multiple potential shortcut rules within the data set, we identify that so also VLPs are not safe from potential shortcut behavior. But you can identify kind of what the potential issue is. So let's say a model is focusing on a wrong color to make its final program for a concept. What you can do is just remove that color from your DSL and have the model kind of find a new solution, but it doesn't have the color anymore to use. So you know that this edit that you've applied in the new solution will definitely not be there anymore. There's like no kind of bleeding or no leakage between other kind of parts of the program and the edit you've done. So again, I think this is very important, not just from the understandability part, but also from the controllability part. So to briefly summarize, I guess, that section as well, we show that by integrating this compositional learning aspect into learning relational concepts from examples works very well and shows also great improvements both on the, I guess, the generalizability side, but then also on the controllability side. But so what's kind of missing? So in this context, we're looking at kind of inductive learning from examples, but there are other forms of reasoning, which is, for example, deductive reasoning, where you're actually given a set of rules. You want to see, okay, what's the final conclusion I can make given these rules, and maybe like the current state of what I'm seeing. So in the next project, we're basically looking at how can we embed kind of compositional logical reasoning directly into more deductive kind of problem-solving settings, where we focus here on actually integrating this into a language model. So why do we want to use language models? Well, so language models are good still in what they do, and I mean the natural language abilities of these models is still very very desirable, I think, in many settings. So what we wanted to do was actually, instead of just replacing the LLM, we want to kind of integrate the compositional logical reasoning into the LLM. Some issues with LLMs, of course, are, and I think many people are aware of this here, that the representations are dense and tangled. And so it's kind of difficult to identify such things as concepts or propositions or compositions within the LLM space. Sparse autoencoders are often used for this to kind of potentially mitigate this disentanglement issue. But SAEs alone don't really provide a mechanism for composition or higher order reasoning. So the question we ask now in this work, led by Lukas Helf and Ruben Herle, was, can we somehow ground logical propositions in this latent space of the LLM using SAEs? And again, the framework is a little bit complex, so I'll go through it step by step. We start with an LM, and we, using an SAE and like potentially already pre-identified concepts, for example, using Neuronpedia, we can build this kind of proposition or concept dictionary, telling us, okay, there are these and these concepts within this SAE space with kind of this feature encoding. So now at inference time, when you get in a new input, you can identify, okay, with what probability or with what kind of score is each concept from this concept dictionary present in my current input. Now, what we do is we, again, kind of outsource the logical reasoning part. So let's say you have a set of rules which you know up front or can somehow deduce from the actual task. And I'll show a few examples of this on the next slide. We turn these rules into kind of just a logical, if you want to say, like a database where you can just do a forward reasoning over these logical rules, telling you, okay, this is the current activation of the concepts. This is what I know about like how concepts are related to another. And this kind of implies that this concept should be present as well, or this concept should not be present as well. And this gives you an updated kind of concept activation space. Now, because we don't want to just remove the LLM entirely, what we actually do in a lot of these tasks is then steer the LLM to update its reasoning process, or to update its kind of next token prediction via the updated concept activation space. So these are a few kind of data sets that we show where this works quite well. These are actually kind of logical data sets where you have multi-hop reasoning, stuff like, I mean, some of these are actually pretty gibberish, like Alex is a lumpus, and lumpuses are dumpuses, and dumpuses are big. What is Alex? And so by transforming this kind of context into a logical form via activation reasoning, and then updating kind of the final concept space and steering the LLM again, you get a very substantial boost in performance, and particularly across multiple hops, where most even thinking models kind of degrade the more hops like the more logical steps you're kind of going. This is also true for like prover QA, which is actually more like a similar kind of setting with like these kind of logical conclusions you're trying to draw, but in a natural language setting. But even here, we can translate this pretty well into like a logical rule or logical kind of database, which we can then use to do the logical reasoning on. So that part, again, I kind of rushed through again. Feel free to ask questions. But overall, I think I'm close to a conclusion. I don't know if I'm on time. I think I'm on time. With this talk, I wanted to kind of motivate or kind of also just put some light on the importance of compositional structure, especially especially for interpretable reasoning. So what we have seen in the previous sections were works where people use different forms of decomposition, either on the task level, on the like object or on the encoding level, on the relational level, on the kind of learning the relational level, but then also on integrating logical reasoning into a model. And these are all different levels and also layers of compositionality. And they all kind of motivate I guess one of the conclusions is that there's no one right unit of composition, but compositionality is important. So I think a big question is just still how should these units be combined for future tasks or differently complex tasks to support both transparency and expressiveness. And then like an open kind of challenge view, I think there are quite a few still. I mean, despite like even these works have still some limitations, which I haven't touched on yet, but kind of having more of a broader view on open challenges, I think an important, one of the most important questions I think for me is also, so how do we know when to decompose a model and what granularity, and how like this should probably be dynamic because it's impossible to do this, like decompose the universe into every part and then just go over that search space, because that's like impossible. The other part, and this is probably more related to the low level decomposition part, is how do we actually ensure that like these compositional units are really encoding the right information or like binding the right information to them, or maybe it's just like correlating them with them. And how do we identify even what this information is? Now, evaluation is always a big topic, I think, particularly in this CBM domain. Many people still focus on the accuracy, me included, and I think we need to focus maybe on a little bit more either truly human user studies or people are proposing other metrics, which I think is very valuable as well. The scaling part, and I hate to be that person who say, how does it scale? But I think it does become quite relevant, especially in these kind of program spaces where you're trying to combine and recombine components. The kind of the combinatorial space can explode pretty quickly. So overall, I think compositionality is a very promising and very important thing to talk about in the topics of like transparency, but also reasoning capability. But of course, this is not the solution to interpretability on its own. But I think it's an important part, which is often like hidden in many approaches. So with that, thanks for listening. And I'd like to thank all my co-authors, which really drove most of these works. And I'm happy for any questions. I don't see anyone, so I don't know what the status is.
Thank you so much, Wolfgang. There's some questions, so I'll start with Aya, who I think raised your hand first.
Very cool work. I just can we go back to the last part you talked about where for the logic reasoning?
Yeah.
I think I might so basically, can you go, so you use the SAE, you have an autoregressive model, right? This is
yes,
a regular LLM.
Exactly, yeah.
And then you get an SAE, extract a Latin representation, and then how do you change the output?
Yeah, so just assuming we already have like this concept dictionary telling us like which feature means what in like human semantics, you're basically like starting from this initial kind of activation space of your concepts. So let's say Golden Gate Bridge was not activated by your initial kind of feature-based concept detection, but Bridge and San Francisco were pretty active. Now let's say you have a rule saying if I know there's a bridge present in the input and San Francisco and in the US is somehow mentioned, then it's probably very likely that the bridge we're talking about is actually the Golden Gate Bridge. I mean, this is somewhat of a constructed example, but let's just say this is the kind of the rule set that we have. So what you do is now forward chaining just through this logical rule. So you basically just append the probabilities for each of these individual atoms or each of these individual components, giving you then the final kind of updated probability of, in this case, Golden Gate. Because we actually do a binarization before this, the updated concept activation space is also binarized. But now you see that, okay, given this rule and kind of this current state of my concepts, I get an updated state for the concept Golden Gate Bridge, which is actually saying that now the Golden Gate is also active.
Okay. Two questions. First, how do we get these logic reasoning rules?
Yeah, so that's always a big question. In this work, I think it's more of a proof of principle showing that just how to integrate, let's say we have these rules, how can we integrate them into the LLM without breaking the LLM, but without without removing these natural language abilities. So in these data sets, particularly, I guess the rules already are in the input. So again, these are like these kind of statements like Alex is a lumpus, so on and so forth. So you get like this paragraph, and you're supposed to deduce something from that. So what we did in this context was just transform the natural language input of each sample and turn that into a logical rule. We also have some experiments in the context of safety where you could argue, okay, I think people know what, or I mean, it depends very much on the culture, on the background, but you might be able to say, I know that this should be considered safe, whereas this should not be considered safe. But it's not a, guns are safe or knives are safe, but in certain contexts they are safe. Sorry, guns are unsafe and knives are unsafe. But in certain contexts, you might be able to argue, I think knives are safe in the context of a kitchen. So by having like these predefined safety rules or this kind of constitution, you can integrate it with activation reasoning to make your LLM actually better at detecting safe or unsafe input.
Okay, so, and let's say you found, okay, we're going to the rule says we should upweight Golden Gate, and then you basically take the activation, you add the Golden Gate bridge to the Latin representation, and then you pass it through the model, right?
Yeah, so actually this is missing kind of in the figure, but we're actually kind of going back here to the LLM and then like updating the LLM's latent space, exactly, yeah.
Okay, very cool. And then what you found that like on the reasoning task, it performs better?
Yes.
These are natural reasoning tasks, right? Like they're all like
the last one is the Pronto QA is still natural language, but this is really like simple text. Like I said, Alex is a lumpus, so it's always this template. It's kind of A is B, B is C, C is D, so on and so forth. So this is natural language, but incredibly simplistic natural language. The prover QA data set, unless I'm mixing up one of the two, I think prover QA is really indeed natural language. Yeah.
Very cool. Okay, thank you so much.
Oh, thank you.
Gabriele, you want to go next?
Hi. So first of all, thank you very much for the very nice talk. I really appreciate it. Let me just say, first of all, I'm a very, very big fan of your works. I read the survey and it was really, really great. I think you did a great job on that.
That's very nice to hear. It took a while to make.
Yeah, I kind of know what you're talking about. We kind of did something similar previously, like a couple of years ago.
Yeah.
But yeah, so and I really appreciate yours. I think yours very, very focused, very, very in depth, very good analysis.
Thank you.
And I was wondering about. I'm also working on. I'm trying to switch to mechanistic interpretability, and I am finding your work super exciting. But at the same time, I am struggling to understand how you can do this. As, for example, myself, I'm experiencing that let's say the huge difficulties in actually associating concepts to specific neurons.
Yeah.
So. Mainly what we are experiencing is that two problems. First of all, we have huge feature splitting. So let's say you may have San Francisco, but you have 10 San Francisco nodes. So you have this that is replicated a lot. And if you don't intervene on all of them at the same time, or you don't get up with something clever, it's super difficult to make any principal intervention. And also, it's super difficult to understand in the sentence, like at which token to intervene, for how much, for how long. So I'm really, really curious on how you did this.
Yeah, so those are very valid points. And so Lucas and Ruben, who did the experiments on this paper, I think they were cursing a lot on these issues. So I think what we also really emphasize in this paper is that we're using SAEs now because this is kind of okay-ish currently, or like one of the ways to go currently. But we also emphasize we're not saying like SAEs are always like kind of the key component within activation reasoning. We just need some kind of, again, concept extractor part here. We're using SAEs for this. But so in our contexts, so either the Neuronpedia entries that we use were already quite good. So for example, in this rail to country thing, this is usually talking about colors. For these kind of concepts, it works quite well. But I think for more complex ones, this is the things you said we observed as well. And I think Lucas and Ruben, they had to do quite a bit of like this kind of targeted label, again, positive, negative set kind of construction to be able to build like these more reliable features. One thing we also did in this context was then actually not just focus on a single feature, but actually we had multiple options on how to represent a concept, going even down to having almost a decision tree over features to represent a specific concept. I think that helped a lot on the robustness. I don't have the results on this. I think they're in the appendix that might be valuable to look at. However, these like complex relational feature representations of a concept were guided by having a more fine-grained kind of input set for that. And I think it's a big issue, not just in SAEs, also in the whole circuit discussion. They're not as good as you need them, so you need to somehow also work with, I think, this probabilistic almost representation, or this probabilistic form of these representations, which I think many works aren't doing yet, but that might be something to maybe look at in like the future. So I don't have an answer to this issue because it's it's an issue.
Yeah, oh, absolutely, but very, very cool. Yeah. So if I can ask just a few more details on the relational latent representation, or that you extract from the feature, was something that was let's say you took from previous work, or something you introduced?
Which one is it? This project or the previous one?
Yeah, no, the relational features here in the latent representation.
No, so again, so this is, so basically we kind of like trained a decision tree classifier for like on the SAE encodings for a specific concept. Okay. So we knew like which concepts specifically we would be interested in, and that's what we were kind of targeting. So this is kind of mitigating the issue of potentially one concept might be represented across multiple features. So what you're doing is you're just kind of doing linear probing for that specific feature, but which still works potentially better within the SAE space than in the LLM space directly.
Cool. Very cool. Okay. Okay. Very nice. Thank you.
Yeah, thank you.
Does anyone else have any other questions? Otherwise, I have one. Sorry to keep asking on the same paper. I have a few of the other ones, but I'll just now that we're on this one, might as well.
The other papers.
As well keep drilling, just because it's the most recent one.
Yeah.
So I see you have sort of in the logical reasoning. I imagine there must be some sort of early units, or early sort of features to use the SAE language that are activated, and then some others like Great Wall of China, Golden Gate, that are sort of function of early features.
Yeah.
And sort of is reminiscent of, like, say, hierarchical essays, like Matryoshka essays, where you sort of decompose intentionally your features into this sort of hierarchy, where you have sort of high level at the first, and then low level, or low level at first, and then high level later down the line.
Yeah.
Did you guys try that? Because I feel like it will naturally map with how you actually sort of do the logical reasoning part of it, where you have certain atoms of the logic that goes early on in the Matryoshka one, and deeper layers will be sort of the more high level atoms of or the grammar.
Yeah, yeah. So no, actually, we did not use Matryoshka in this paper. I think just no particular reason. But I think even if you use Matryoshka, the point is still, I mean, I don't think a Matryoshka SAE will ever, like, already in its encodings contain all the possible, like, compositions of more complex concepts. So I think even if you use Matryoshka, potentially parts of these, like, mid-level concepts are already encoded in Matryoshka space.
Mm-hmm.
But the point is here, I think there are, depending on the task, there are always going to be concepts which you can compose from lower level ones, but which are not represented even in your SAE space yet. Or, you know, there was some kind of error in the forward processing of your LLM. So yeah, I think even if you use in the Matryoshka, there might be some, or I'm assuming there's gonna be benefits of also integrating this logical, compositional logical side into the LLM. Okay,
no, cool. And then I guess more of a technical sort of aspect of that, I was wondering, like, at what point of the sort of auto generation, the generation do you apply this? You apply it every step after the sort of initial query has been done, and you keep generating, or is it like how does this work in practice? Like the actual steering.
Which token step?
Yeah, exactly. So you do it for every token after you've given your initial prompt, or you do it, like, how do you decide when to do it?
Yeah. So here we do it, like, given the initial prompt. I mean, essentially also here, I mean, in principle, this should work for any, like, next token prediction thing. The tasks we're looking at here, they usually require just like a single word answer.
Okay.
So like so you have, again, using this Alex as a Dumpus example, in the end, so you have the context, Alex is blah, 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 blah. And then the kind of the question is now Alex is now space. And so the LLM should be predicting what Alex is. So it's really just that final token that we're doing it on.
And then
you could be doing this for every kind of token, but I mean, you don't, and I think this is also a relevant topic in the whole concept-based reasoning. I mean, you don't always, for every token, I mean, if you're predicting I don't need to know what's the concept probably I'm using for that. So here we're kind of using the data sets that are simple enough to just use it, like the final word that we're predicting. Again, going back to this kind of dynamic decomposition thing, I think we need to identify when we need to really then apply this and when not, because you definitely do not need this every step.
Yeah, and because then I guess I'll not finish this, so I don't want to take too much of your time, but because I was wondering, because if it's one single token, then I guess you can evaluate in two ways. You can actually generate a token and then see how likely, how often that's the correct token, or you can just look at the probabilities of all the options. You know, that's quite common when you use, for example, multiple answer questions, where you have to check whether A to D is the correct answer. You check the probabilities across.
Yeah.
So do you actually generate the language? Like, do you actually generate a token, or do you just look at the probability of the possible tokens that you expect and look at the maximum there?
Oof. I have to check the paper on how we did that.
Because the reason I'm asking is because I'm curious how this affects the language generation of the model itself. So if you just put this in the model and then ask, you know, like, what's your favorite color? how much was this affecting that when it was not for the task that you were looking into?
Well, I mean, I guess what you can argue here is that you're kind of turning this on or off whenever you need it. So if you don't need it, you're not influencing the language abilities of the model, right?
Yeah, absolutely. No, it's just I understand it perfectly, like in the sense of like that makes a lot of sense. I'm just curious to like how this affected just the general capabilities of the model to generate natural language in
Good question, and I don't think we even had evaluations on that. We probably should have. Yeah, so I don't have an answer on that. We'll have to look at that.
But maybe expressive. I think for this instance, this is exactly, it's a proof of concept of exactly what you guys were arguing, so it makes sense.
Yeah.
I was just curious if you play around with it.
Yeah.
All right, I think we're on time. I don't know if anyone has any last minute questions. If so, please shout. All right. Otherwise, thank you so much, Wolfgang. It's been amazing. Really appreciate it.
Thank you.
Thanks for listening.
Thank you.
Yeah.
And yeah, we'll see you guys next week, same time as always. And see you then. Thank you, man.
Ciao, ciao.
Bye-bye.
Bye.
Bye.